You've announced the integration of ChatGPT and Wolfram Alpha and Wolfram Language. So let's talk about that integration. What are the key differences from the high philosophical level, maybe the technical level, between the capabilities of, broadly speaking, the two kinds of systems, large language models and this gigantic computational system infrastructure that is Wolfram Alpha?
Yeah. So what does something like ChatGPT do? It's mostly focused on make language like the language that humans have made and put on the web and so on.
Yeah.
So, its primary sort of underlying technical thing is you've given a prompt. It's trying to continue that prompt in a way that's somehow typical of what it's seen based on 1 trillion words of text that humans have written on the web. And the way it's doing that is with something which is probably quite similar to the way we humans do the first stages of that, using a neural net and so on, and just saying, given this piece of text, let's ripple through the neural net one word and get one word at a time of output. And it's kind of a shallow computation on a large amount of kind of training data that is what we humans have put on the web. That's a different thing from sort of the computational stack that I've spent the last, 40 years or so building, which has to do with what can you compute many steps, potentially a very deep computation. It's not sort of taking the statistics of what we humans have produced and trying to continue things based on that statistics. Instead, it's trying to take kind of the formal structure that we've created in our civilization, whether it's from mathematics or whether it's from kind of systematic knowledge of all kinds, and use that to do arbitrarily deep computations to figure out things that aren't just let's match what's already been kind of said on the web, but let's potentially be able to compute something new and different that's never been computed before. So as a practical matter, our goal is to have made as much as possible of the world computable, in the sense that if there's a question that in principle is answerable from some sort of expert knowledge that's been accumulated, we can compute the answer to that question, and we can do it in a sort of reliable way that's the best one can do given what the expertise that our civilization has accumulated. It's a much more sort of labor intensive on the side of kind of creating kind of the computational system to do that. Obviously, in the kind of the ChatGPT world, it's like take things which were produced for quite other purposes, namely all the things we've written out on the web and so on, and sort of forage from that things which are like what's been written on the web. So I think, as a practical point of view, I view sort of the ChatGPT thing as being wide and shallow, and what we're trying to do with sort of building out computation as being this sort of deep, also broad, but most importantly, kind of deep type of thing. I think another way to think about this is if you go back in human history, 1,000 years or something, and you say, what can the typical person, what's the typical person going to figure out? Well, the answer is there's certain kinds of things that we humans can quickly figure out. That's sort of what our at our neural architecture and the kinds of things we learn in our lives let us do. But then there's this whole layer of kind of formalization that got developed which is, the kind of whole sort of story of intellectual history and whole kind of depth of learning. That formalization turned into things like logic, mathematics, science, and so on. And that's the kind of thing that allows one to kind of build these towers of sort of towers of things you work out. It's not just, I can immediately figure this out. It's, no, I can use this kind of formalism to go step by step and work out something which was not immediately obvious to me. And that's kind of the story of what we're trying to do computationally, is to be able to build those kind of tall towers of what implies what, and so on. As opposed to kind of yes, I can immediately figure it out. It's just like what I saw somewhere else in something that I heard or remembered or something like this.
What can you say about the kind of formal structure, or the kind of formal foundation you can build such a formal structure on? About the kinds of things you would start on in order to build this kind of deep computable knowledge trees?
So the question is sort of how do you think about computation? And there's a couple of points here. One is what computation intrinsically is like, and the other is what aspects of computation we humans with our minds and with the kinds of things we've learnt can sort of relate to in that computational universe. So if we start on the kind of what can computation be like, it's something I've spent some big chunk of my life studying, is imagine that we usually write programs where we kind of know what we want the program to do, and we carefully write many lines of code, and we hope that the program does what we intended it to do. But the thing I've been interested in is if you just look at the kind of natural science of programs. So you just say, I'm going to make this program. It's a really tiny program. Maybe I even pick the pieces of the program at random, but it's really tiny. And by really tiny, I mean, less than a line of code type thing. Mm-hmm. You say, what does this program do? And you run it. And big discovery that I made in the early 80s is that even extremely simple programs, when you run them, can do really complicated things. It really surprised me. It took me several years to kind of realize that that was a thing, so to speak. But that realization that even very simple programs can do incredibly complicated things that we very much don't expect. That discovery, I realized that that's very much, I think, how nature works. That is, nature has simple rules, but yet does all sorts of complicated things that we might not expect. As a big thing of the last few years has been understanding that that's how the whole universe and physics works. But that's a quite separate topic. But so there's this whole world of programs and what they do, and very rich, sophisticated things that these programs can do. But when we look at many of these programs, we look at them and say, well, that's kind of, I don't really know what that's doing. It's not a very human kind of thing. So on the one hand, we have sort of what's possible in the computational universe. On the other hand, we have the kinds of things that we humans think about, the kinds of things that are developed in kind of our intellectual history. And that's really the challenge to sort of making things computational is to connect what's computationally possible out in the computational universe with the things that we humans sort of typically think about with our minds. Now, that's a complicated kind of moving target because the things that we think about change over time. We've learned more stuff. We've invented mathematics. We've invented various kinds of ideas and structures and so on. So it's gradually expanding. We're kind of gradually colonizing more and more of this kind of intellectual space of possibilities. But the real thing, the real challenge is how do you take what is computationally possible? How do you encapsulate the kinds of things that we think about in a way that kind of plugs into what's computationally possible? And actually the big sort of idea there is this idea of kind of symbolic programming, symbolic representations of things. And so the question is, when you look at sort of everything in the world and you kind of, you take some visual scene or something you're looking at, and then you say, well, how do I turn that into something that I can kind of stuff into my mind? There are lots of pixels in my visual scene, but the things that I remembered from that visual scene are, there's a chair in this place. Mm-hmm. It's a kind of a symbolic representation of the visual scene. There are two chairs and a table or something, rather than there are all these pixels arranged in all these detailed ways. And so the question then is, how do you take sort of all the things in the world and make some kind of representation that corresponds to the types of ways that we think about things? And human language is sort of one form of representation that we have. We talk about chairs, that's a word in human language and so on. How do we take, but human language is not in and of itself something that plugs in very well to sort of computation. It's not something from which you can immediately compute consequences and so on. And so you have to kind of find a way to take sort of the stuff we understand from human language and make it more precise. And that's really this story of symbolic programming. And what that turns into is something which I didn't know at the time it was going to work as well as it has. But back in the 1979 or so, I was trying to build my first big computer system and trying to figure out, how should I represent computations at a high level? And I kind of invented this idea of using kind of symbolic expressions, structured as it's kind of like a function and a bunch of arguments. But that function doesn't necessarily evaluate to anything. It's just a thing that sits there representing a structure. And so building up that structure, and it's turned out that structure has been it's a good match for the way that we humans, it seems to be a good match for the way that we humans kind of conceptualize higher level things. And it's been for the last, 45 years or something. It's served me remarkably well.
So building up that structure using this kind of symbolic representation. But what can you say about abstractions here? Because you could just start with your physics project. You could start at a hypergraph at a very, very low level and build up everything from there, but you don't. You take shortcuts.
Right.
You take the highest level of abstraction, convert that, the kind of abstraction that's convertible into something computable using symbolic representation. And then that's your new foundation for that little piece of knowledge.
Yes.
And somehow all of that is integrated.
Right. So the sort of a very important phenomenon that is kind of a thing that I've sort of realized is just, it's one of these things that sort of in the future of kind of everything is going to become more and more important, is this phenomenon of computational irreducibility. And the question is, if you know the rules for something, you have a program, you're going to run it, you might say, I know the rules. Great. I know everything about what's going to happen. Well, in principle, you do, because you can just run those rules out and just see what they do. You might run them a million steps, you see what happens, etc. The question is, can you immediately jump ahead and say, I know what's going to happen after a million steps, and the answer is 13 or something?
Yes.
And the one of the very critical things to realize is, if you could reduce that computation, there is, in a sense, no point in doing the computation. Yeah. The place where you really get value out of doing a computation is when you had to do the computation to find out the answer. But this phenomenon that you have to do the computation to find out the answer, this phenomenon of computational irreducibility, seems to be tremendously important for thinking about lots of kinds of things. So one of the things that happens is, okay, you've got a model of the universe at the low level in terms of atoms of space and hypergraphs and rewriting of hypergraphs and so on. And it's happening, 10 to the 100 times every second, let's say. Well, you say, great, then we've nailed it. We know how the universe works. Well, the problem is the universe can figure out what it's going to do. It does those 10 to the 100, steps. But for us to work out what it's going to do, we have no way to reduce that computation. The only way to do the computation, to see the result of the computation, is to do it. And if we're operating within the universe, we're kind of, there's no opportunity to do that, because the universe is doing it as fast as the universe can do it. Mm-hmm. And that's what's happening. So what we're trying to do, and a lot of the story of science and a lot of other kinds of things, is finding pockets of reducibility. Mm-hmm. That is, you could have a situation where everything in the world is full of computational irreducibility. We never know what's going to happen next. The only way we can figure out what's going to happen next is just let the system run and see what happens. So in a sense, the story of most kinds of science, inventions, a lot of kinds of things, is the story of finding these places where we can locally jump ahead. Mm-hmm. And one of the features of computational irreducibility is there are always pockets of reducibility. There are always an infinite number of places where you can jump ahead. There's no way where you can jump completely ahead, but there are little patches, little places where you can jump ahead a bit. And I think, we can talk about physics project and so on, but I think the thing we realize is we kind of exist in a slice of all the possible computational irreducibility in the universe. We exist in a slice where there's a reasonable amount of predictability. And in a sense, as we try and construct these kind of higher levels of abstraction, symbolic representations and so on, what we're doing is we're finding these lumps of reducibility that we can kind of attach ourselves to, and about which we can kind of have fairly simple narrative things to say. Because in principle, I say, what's going to happen in the next few seconds? There are these molecules moving around in the air in this room, and oh gosh, it's an incredibly complicated story. And that's a whole computationally irreducible thing, most of which I don't care about. Mm-hmm. And most of it is, the air's still going to be here and nothing much is going to be different about it. And that's a kind of reducible fact about what is ultimately at an underlying level a computationally irreducible process.
And life would not be possible if we didn't have a large number of such reducible pockets.
Yes.
Pockets amenable to reduction into something symbolic.
Yes, I think so. I mean, life in the way that we experience it, one might, depending on what we mean by life, so to speak, the experience that we have of sort of consistent things happening in the world the idea of space, for example, where there's, we can just say, you're here, you move there. It's kind of the same thing. It's still you in that different place, even though you're made of different atoms of space and so on. This is this idea that it's that there's sort of this level of predictability of what's going on. That's us finding a slice of reducibility in what is underneath this computationally irreducible kind of system. And I think that's sort of the thing which is actually my favorite discovery of the last few years is the realization that it is sort of the interaction between this sort of underlying computational irreducibility and our nature as kind of observers who sort of have to key into computational reducibility. Mm-hmm. That fact leads to the main laws of physics that we discovered in the 20th century. So we talk about this in more detail, but this is to me, it's kind of our nature as observers, the fact that we are computationally bounded observers. We don't get to follow all those little pieces of computational irreducibility. To stuff what is out there in the world into our minds requires that we are looking at things that are reducible. We are compressing, we're extracting just some essence, some kind of symbolic essence of what's the detail of what's going on in the world. That, together with one other condition that at first seems sort of trivial, but isn't, which is that we believe we are persistent in time. That is,
yes. So some sense of causality.
Here's the thing. At every moment, according to our theory, we're made of different atoms of space. At every moment, sort of the microscopic detail of what the universe is made of is being rewritten. Mm-hmm. And in fact, the very fact that there's coherence between different parts of space is a consequence of the fact that there are all these little processes going on that kind of knit together the structure of space. It's kind of like if you wanted to have a fluid with a bunch of molecules in it, if those molecules weren't interacting, you wouldn't have this fluid that would pour and do all these kinds of things. It would just be sort of a free-floating collection of molecules. Mm-hmm. So similarly it is with space, that the fact that space is kind of knitted together is a consequence of all this activity in space. And the fact that kind of what we consist of, sort of this series of we're continually being rewritten. And the question is, why is it the case that we think of ourselves as being the same us through time? That's kind of a key assumption. I think it's a key aspect of what we see as sort of our consciousness, so to speak, mm-hmm. is that we have this kind of consistent thread of experience.
Well, isn't that just another limitation of our mind, that we want to reduce reality into some, that kind of temporal consistency is just a nice narrative to tell ourselves.
Well, the fact is, I think it's critical to the way we humans typically operate, is that we have this single thread of experience. If you imagine sort of a mind where you have, maybe that's what's happening in various kinds of minds that aren't working the same way other minds work, is that you're splitting into multiple threads of experience. It's also something where, when you look at, quantum mechanics, for example, in the insides of quantum mechanics, it's splitting into many threads of experience. But in order for us humans to interact with it, you kind of have to knit all those different threads together so that we say, oh yeah, a definite thing happened, and now the next definite thing happens, and so on. And I think, sort of inside, it's sort of interesting to try and imagine what's it like to have kind of these fundamentally multiple threads of experience going on. I mean, right now, different human minds have different threads of experience. We just have a bunch of minds that are interacting with each other, but we don't have within each mind, there's a single thread. And that is indeed a simplification. I think it's a thing, the general computational system does not have that simplification. Mm-hmm. And it's one of the things, people often seem to think that, consciousness is the highest level of kind of things that can happen in the universe, so to speak. But I think that's not true. I think it's actually a specialization in which, among other things, you have this idea of a single thread of experience, which is not a general feature of anything that could kind of computationally happen in the universe.
So it's a feature of a computationally limited system that's only able to observe reducible pockets. So I mean, this word observer, it means something in quantum mechanics. It means something in a lot of places. It means something to us humans.
Right.
as conscious beings. So what's the importance of the observer? What is the observer, and what's the importance of the observer in the computational universe?
So this question of what is an observer, what's the general idea of an observer, is actually one of my next projects, which got somewhat derailed by the current sort of AI mania. But
is there a connection there, or is that do you think the observer is primarily a physics phenomena?
is it related to the whole AI thing?
Yes.
Yes, it is related. So one question is, what is a general observer?
Mm-hmm.
So, we have an idea what is a general computational system. We think about Turing machines. We think about other models of computation. There's a question, what is a general model of an observer? And there's kind of observers like us, which is kind of the observers we're interested in.
Yeah.
We could imagine an alien observer that deals with computational irreducibility, and it has a mind that's utterly different from ours and completely incoherent with what we're like. But the fact is that if we are talking about observers like us, that one of the key things is this idea of kind of taking all the detail of the world and being able to stuff it into a mind, being able to take all the detail and kind of extract out of it a smaller set of kind of degrees of freedom, a smaller number of elements that will sort of fit in our minds. And I think this question, so I've been interested in trying to characterize what is the general observer. And the general observer is, I think, in part, there are many, let me give an example of you have a gas, it's got a bunch of molecules bouncing around, and the thing you're measuring about the gas is its pressure.
Mm-hmm.
And the only thing you as an observer care about is pressure. And that means you have a piston on the side of this box, and the piston is being pushed by the gas. And there are many, many different ways that molecules can hit that piston. But all that matters is the kind of aggregate of all those molecular impacts, because that's what determines pressure. So there's a huge number of different configurations of the gas, which are all equivalent. So I think one key aspect of observers is this equivalencing of many different configurations of a system, saying all I care about is this aggregate feature. All I care about is this overall thing. And that's sort of one aspect. And we see that in lots of different, again, it's the same story over and over again, that there's a lot of detail in the world, but what we are extracting from it is something, sort of a thin summary of that detail.
Is that thin summary nevertheless true? Can it be a crappy approximation?
Sure.
That on average is correct? I mean, if we look at the observer that's the human mind, it seems like there's a lot of very, as represented by natural language, for example, there's a lot of really crappy approximation.
Sure.
And that could be maybe a feature of it.
Well,
that there's ambiguity.
Right. You don't know. It could be the case. You're just measuring the aggregate impacts of these molecules, but there is some tiny, tiny probability that the molecules will arrange themselves in some really funky way, and that just measuring that average isn't going to be the main point.
Yeah.
By the way, an awful lot of science is very confused about this because you look at papers and people are really keen. They draw this curve and they have these these bars on the curve and things. Yeah. And it's just this curve, and it's this one thing. And it's supposed to represent some system that has all kinds of details in it. And this is a way that lots of science has gotten wrong. Because people say, I remember years ago I was studying snowflake growth. You have the snowflake and it's growing, it has all these arms, it's doing complicated things. But there was a literature on this stuff, and it talked about, what's the rate of snowflake growth? And, it got pretty good answers for the rate of the growth of the snowflake. And they looked at it more carefully, and they had these nice curves of, snowflake growth rates and so on. I looked at it more carefully, and I realized, according to their models, the snowflake will be spherical.
Mm-hmm.
And so they got the growth rate right, but the detail was just utterly wrong. And not only the detail, the whole thing was not capturing. It was capturing this aspect of the system that was, in a sense, missing the main point of what was going on. And
what is the geometric shape of a snowflake?
Snowflakes start in the phase of water that's relevant to the formation of snowflakes. It's a phase of ice which starts with a hexagonal arrangement of water molecules. Mm-hmm. And so it starts off growing as a hexagonal plate. And then what happens is
it's a plate. Versus sphere versus
well, no,
plate.
But it's much more than that. I mean, snowflakes are fluffy. Typical snowflakes have little dendritic arms.
Okay, yeah.
And what actually happens is it's kind of cool because you can make these very simple discrete models with cellular automata and things that figure this out. You start off with this hexagonal thing, and then the places it starts to grow little arms. And every time a little piece of ice adds itself to the snowflake, the fact that that ice condensed from the water vapor heats the snowflake up locally. And so it makes it less likely for another piece of ice to accumulate right nearby. So this leads to a kind of growth inhibition. So you grow an arm, and it is a separated arm because right around the arm, it got a little bit hot and it didn't add more ice there. So what happens is it grows, you have a hexagon, it grows out arms, the arms grow arms, and then the arms grow arms, grow arms. And eventually, actually, it's kind of cool because it actually fills in another hexagon, a bigger hexagon. And when I first looked at this, I had a very simple model for this. I realized, when it fills in that hexagon, it actually leaves some holes behind. So I thought, well, is that really right? So I look at these pictures of snowflakes, and sure enough, they have these little holes in them that are kind of scars of the way that these arms grow out.
So you can't fill in backfill holes. So
they don't backfill. Yeah, they don't backfill.
And presumably there's a limitation of how big, like you can't arbitrarily grow.
I'm not sure. I mean, the thing falls through I think it does, it hits the ground at some point. I think you can grow, I think you can grow in the lab. I think you can grow pretty big ones. I think you can grow many, many iterations of this kind of, goes from the hexagon, it grows out arms, it fills back into a hexagon, it grows more arms again.
In 3D?
No, it's flat usually.
Why is it flat? Why doesn't it span out? Okay, wait a minute. You said it's fluffy, and fluffy is a three-dimensional property, no? Or
no, it's fluffy. Snow is okay. So what makes we're really in a detail here, but
there's multiple snowflakes become fluffy. A single snowflake is not fluffy.
No, a single snowflake is fluffy. And what happens is, if you have snow that is just pure hexagons, they can, they fit together pretty well. It doesn't have a lot of air in it. And they can also slide against each other pretty easily. And so the snow can be pretty, I think avalanches happen sometimes when the things tend to be these, hexagonal plates, and it kind of slides. But then when the thing has all these arms that have grown out, they don't fit together very well. And that's why the snow has lots of air in it. And if you look at one of these snowflakes, if you catch one, you'll see it has these little arms. And people often say, no two snowflakes are alike. That's mostly because as a snowflake grows, they do grow pretty consistently with these different arms and so on, but you capture them at different times. As they fell through the air in a different way, you'll catch this one at this stage, and as it goes through different stages, they look really different. And so that's why, kind of looks like no two snowflakes are alike, because you caught them at different times.
So the rules under which they grow are the same. It's just the timing is.
Yes.
Okay, so the point is science is not able to describe the full complexity of snowflake growth.
Well, science, if you do what people might often do, which is say, okay, let's make it scientific, let's turn it into one number. And that one number is kind of the growth rate of the arms or some such other thing. That fails to capture sort of the detail of what's going on inside the system. And that's, in a sense, a big challenge for science, is how do you extract from the natural world, for example, those aspects of it that you are interested in talking about. Now, you might just say, I don't really care about the fluffiness of the snowflakes. All I care about is the growth rate of the arms, in which case, you can have a good model without knowing anything about the fluffiness. But the fact is, as a practical, if you say, what is the most obvious feature of a snowflake? Oh, that it has this complicated shape. Well, then you've got a different story about what you model. I mean, this is one of the features of sort of modeling in science, that, what is a model? A model is some way of reducing the actuality of the world to something where you can readily sort of give a narrative for what's happening, where you can basically make some kind of abstraction of what's happening and answer questions that you care about answering. If you wanted to answer all possible questions about the system, you'd have to have the whole system, because you might care about this particular molecule. Where did it go? And, your model, which is some big abstraction of that, has nothing to say about that. So, one of the things that's often confusing in science is people will have, I've got a model, somebody says. Somebody else will say, I don't believe in your model because it doesn't capture the feature of the system that I care about. There's always this controversy about, is it a correct model? Well, no model except for the actual system itself is a correct model in the sense that it captures everything. The question is, does it capture what you care about capturing? Sometimes that's ultimately defined by what you're going to build technology out of, things like this. The one counterexample to this is if you think you're modeling the whole universe all the way down, then there is a notion of a correct model. But even that is more complicated because it depends on kind of how observers sample things and so on. That's a separate story. But at least at the first level, to say, this thing about, it's an approximation, you're capturing one aspect, you're not capturing other aspects. When you really think you have a complete model for the whole universe, you better be capturing ultimately everything, even though to actually run that model is impossible because of computational irreducibility. The only thing that successfully runs that model is the actual running of the universe.
Is the universe itself. But okay, so what you care about is an interesting concept. So that's a human concept. So that's what you're doing with Wolfram Alpha and Wolfram Language, is you're trying to come up with symbolic representations,
yes,
as simple as possible. So a model that's as simple as possible that fully captures stuff we care about.
Yes. So, I mean, for example, we'll have a thing about, data about movies, let's say. We could be describing every individual pixel in every movie and so on, but that's not the level that people care about. And and that level that people care about is somewhat related to what's described in natural language. Mm-hmm. But what we're trying to do is to find a way to sort of represent precisely so you can compute things. See, one thing when you say, you give a piece of natural language, question is, you feed it to a computer. You say, does the computer understand this natural language? Well, the computer processes it in some way. It does this. Maybe it can make a continuation of the natural language. Maybe it can go on from the prompt and say what it's going to say. You say, does it really understand it? Hard to know. But in this kind of computational world, there is a very definite definition of does it understand, which is, could it be turned into this symbolic computational thing from which you can compute all kinds of consequences? Mm-hmm. And that's the sense in which one has sort of a target for the understanding of natural language. And that's kind of our goal, is to have as much as possible about the world that can be computed in a reasonable way, so to speak, be able to be sort of captured by this kind of computational language. That's kind of the goal. And I think for us humans, the main thing that's important is, as we formalize what we're talking about, it gives us a way of kind of building a structure where we can sort of build this tower of consequences of things. So if we're just saying, well, let's talk about it in natural language, it doesn't really give us some hard foundation that lets us, build step by step to work something out. I mean, it's kind of like what happens in math. If we were just sort of vaguely talking about math, but didn't have the kind of full structure of math and all that kind of thing, we wouldn't be able to build this kind of big tower of consequences. And so, in a sense, what we're trying to do with the whole computational language effort is to make a formalism for describing the world that makes it possible to kind of build this tower of consequences.
Well, can you talk about this dance between natural language and Wolfram language? So there's this gigantic thing we call the internet, where people post memes and diary type thoughts and very important sounding articles and all of that makes up the training data set for GPT. And then there's Wolfram language. How can you map from the natural language of the internet to the Wolfram language? Is there an manual? Is there an automated way of doing that as we look into the future?
Well, so Wolfram Alpha, what it does, its kind of front end is turning natural language into computational language.
Right. What you mean by that is there's a prompt, you ask a question, what is the capital of some country?
Right. And it turns into, what's the distance between, Chicago and London or something? Yeah. And that will turn into, geodistance of entity, city, et cetera, et cetera, et cetera. Each one of those things is very well defined. We know, given that it's the entity, city, Chicago, et cetera, et cetera, et cetera, Illinois, United States, we know the geolocation of that. We know its population. We know all kinds of things about it, mm-hmm. which we have, curated that data to be able to know that with some degree of certainty, so to speak. Mm-hmm. And then we can compute things from this, and that's kind of that's the idea.
But then something like GPT, large language models, do they allow you to make that conversion much more powerful?
Okay, so that's an interesting thing, which we still don't know everything about. Okay, this question of going from natural language to computational language.
Yes.
In Wolfram Alpha, we've now, Wolfram Alpha's been out and about for 13 and a half years now. And, we've achieved, I don't know what it is, 98%, 99% success on queries that get put into it. Now, obviously, there's a sort of feedback loop because the things that work are things people go on putting into it. So but we've got to a very high success rate of the little fragments of natural language that people put in, questions, math calculations, chemistry calculations, whatever it is. We do very well at that, turning those things into computational language. Now, from the very beginning of Wolfram Alpha, I thought about, for example, writing code with natural language. In fact, I was just looking at this recently. I had a post that I wrote in 2010, 2011 called something like "Programming with Natural Language is Actually Going to Work." Mm-hmm. Okay. And so, we had done a bunch of experiments using methods that were a little bit, some of them a little bit machine learning like, but certainly not the same kind of idea of vast training data and so on. Mm-hmm. That is the story of large language models. Actually, I know that post, a piece of utter trivia, but that post, Steve Jobs forwarded that post around to all kinds of people at Apple. Mm-hmm. And that was because he never really liked programming languages. So he was very happy to see the idea that you could get rid of this kind of layer of kind of engineering-like structure. He would have liked, I think what's happening now, because it really is the case that you can, this idea that you have to kind of learn how the computer works to use a programming language is something that is, I think, a thing that, just like you had to learn the details of the opcodes to know how assembly language worked and so on. It's kind of a thing that's a limited time horizon. But kind of so this idea of how elaborate can you make kind of the prompt, how elaborate can you make the natural language and abstract from it computational language? It's a very interesting question. And, what ChatGPT, GPT-4 and so on can do is pretty good. It's a very interesting process. I'm still trying to understand this workflow. We've been working out a lot of tooling around this workflow.
From natural language to computational language.
Right.
And the process, especially if it's conversation, like dialogue. It's like multiple queries kind of thing.
Yeah, right. There's so many things that are really interesting that work and so on. So first thing is, can you just walk up to the computer and expect to sort of specify a computation? What one realizes is humans have to have some idea of kind of this way of thinking about things computationally. Mm-hmm. Without that, you're kind of out of luck because you just have no idea what you're going to walk up to a computer. I remember when I should tell a silly story about myself. The very first computer I saw, mm-hmm. which was when I was 10 years old, and it was a big mainframe computer and so on. And I didn't really understand what computers did. And it's like somebody was showing me this computer and it's like, can the computer work out the weight of a dinosaur? Mm-hmm. It's like, that isn't a sensible thing to ask. Mm-hmm. That's kind of, you have to give it. That's not what computers do. I mean, in Wolfram Alpha, for example, you could say, what's the typical weight of a stegosaurus? And it will give you some answer. But that's a very different kind of thing from what one thinks of computers as doing. And so the question of, first thing is people have to have an idea of what computation is about. I think it's a very, for education, that is the key thing. Is kind of this notion, not computer science, not so the details of programming, but just this idea of how do you think about the world computationally. Thinking about the world computationally is kind of this formal way of thinking about the world. We've had other ones, like logic was a formal way, is a way of sort of abstracting and formalizing some aspects of the world. Mathematics is another one. Computation is this very broad way of sort of formalizing the way we think about the world. And the thing that's cool about computation is if we can successfully formalize things in terms of computation, computers can help us figure out what the consequences are. It's not like you formalized it with math. Well, that's nice, but now you have to, if you're not using a computer to do the math, you have to go work out a bunch of stuff yourself. So I think, but this idea, let's see, we're trying to take kind of we're talking about sort of natural language and its relationship to computational language. The typical workflow, I think, is first human has to have some kind of idea of what they're trying to do. That if it's something that they want to sort of build a tower of capabilities on, something that they want to sort of formalize and make computational. So then human can type something into, some LLM system and sort of say vaguely what they want in sort of computational terms. Then it does pretty well at synthesizing Wolfram language code. And it'll probably do better in the future because we've got a huge number of examples of natural language input together with the Wolfram language translation of that. Mm-hmm. So it's kind of that's a thing where you can kind of extrapolating from all those examples makes it easier to do that task.
Is the prompter task also kind of debugging the Wolfram language code? Or is your hope to not do that debugging?
Oh, no. I mean, so there are many steps here. Okay, yeah. So the first thing is you type natural language. It generates Wolfram language code.
Do you have examples, by the way? Do you have an example that, is it the dinosaur example? Do you have an example that jumps to mind that we should be thinking about, some dumb example?
It's like, take my heart rate data and, figure out whether I... make a moving average every 7 days or something and work out what the, and make a plot of the result. Mm-hmm. Okay. So that's a thing which is, about 2/3 of a line of Wolfram language code. Mm-hmm. I mean, it's, list plot of moving average of some data bin or something of the data, mm-hmm. and then you'll get the result. And, the vague thing that I was just saying in natural language would almost certainly correctly turn into that very simple piece of Wolfram language code.
Mm-hmm. So you start mumbling about heart rate.
Yeah.
And kind of, you arrive at the moving average kind of idea.
Right. You say average over 7 days. Maybe it'll figure out that that's a moving, that can be encapsulated as this moving average idea. I'm not sure. But then the typical workflow that I'm seeing is you generate this piece of Wolfram language code. It's pretty small usually. And if it isn't small, it probably isn't right. But if it's pretty small, and Wolfram language is one of the ideas of Wolfram language is it's a language that humans can read. It's not a language which programming languages tend to be this one-way story of humans write them and computers execute from them. Wolfram language is intended to be something which is sort of like math notation, something where humans write it and humans are supposed to read it as well. And so kind of the workflow that's emerging is kind of this human mumbles some things, large language model produces a fragment of Wolfram language code, then you look at that, you say, yeah, that looks, well, typically you just run it first. You see, does it produce the right thing? You look at what it produces, you might say that's obviously crazy. You look at the code, I see why it's crazy. You fix it. If you really care about the result and you really want to make sure it's right, you better look at that code and understand it, because that's the way you have this sort of checkpoint of, did it really do what I expected it to do? Now, you go beyond that. I mean, it's what we find is, for example, let's say the code does the wrong thing. Mm-hmm. Then you can often say to the large language model, can you adjust this to do this? And it's pretty good at doing that.
Interesting. So you're using the output of the code to give you hints about the function of the code. So you're debugging based on the output of the code, not the code itself.
Right. The plugin that we have, for ChatGPT, it does that routinely. It will send the thing in, it will get a result. The LLM will discover itself that the result is not plausible. Mm-hmm. And it will go back and say, oh, I'm sorry, it's very polite. And it goes back and says, I'll rewrite that piece of code. And then it will try it again and get the result. The other thing that's pretty interesting is when you're just running. So one of the new concepts that we invented this whole idea of notebooks back 36 years ago now. Mm-hmm. And so now there's the question of sort of how do you combine this idea of notebooks where you have, text and code and output. How do you combine that with the notion of chat and so on? And there's some really interesting things there. Like, for example, a very typical thing now is we have these notebooks where as soon as if the thing produces errors, if run this code and it produces messages and so on, the the LLM automatically not only looks at those messages, it can also see all kinds of internal information about stack traces and things like this. And it does a remarkably good job of guessing what's wrong and telling you. So in other words, it's looking at things. It's sort of interesting. It's kind of a typical sort of AI-ish thing that it's able to have more sensory data than we humans are able to have, because it's able to look at a bunch of stuff that we humans would kind of glaze over looking at. And it's able to then come up with, oh, this is the explanation of what's happening.
And what is the data? The stack trace, the code you've written previously, the natural language you've written previously?
Yeah, it's also what's happening is one of the things that's is, for example, when there's these messages, there's documentation about these messages, there's examples of where the messages have occurred otherwise.
Nice.
All these kinds of things. The other thing that's really amusing with this is when it makes a mistake, one of the things that's in our prompt when the code doesn't work is read the documentation. And we have another piece of the plugin that lets it read documentation. And that, again, is very, very useful because it will figure out, sometimes it'll make up the name of some option for some function that doesn't really exist, read the documentation. It'll have, some wrong structure for the function and so on. That's a powerful thing. I mean, the thing that, I've realized is we built this language over the course of all these years to be nice and coherent and consistent and so on, so it's easy for humans to understand. Turns out there was a side effect that I didn't anticipate, which is it makes it easier for AIs to understand.
So it's almost like another natural language. But
yeah.
So Wolfram language is a kind of foreign language.
Yes.
So
yes.
You have a lineup: English, French, Japanese, Wolfram language, and then I don't know, Spanish. And then the system is not going to notice. Hopefully.
Well, yes. I mean, maybe. That's an interesting question because it really depends on what I see as being an important piece of fundamental science that basically just jumped out at us with ChatGPT. Because I think, the real question is, why does ChatGPT work? How is it possible to encapsulate, to successfully reproduce all these kinds of things in natural language? With a comparatively small, he says, couple of 100 billion, weights of neural net and so on. And I think that, that relates to kind of a fundamental fact about language, which, the main thing is that I think there's a structure to language that we haven't kind of really explored very well. It's kind of this semantic grammar I'm talking about language. I mean, we kind of know that when we set up human language, we know that it has certain regularities. We know that it has a certain grammatical structure, noun followed by verb, followed by noun, adjectives, et cetera, et cetera, et cetera. That's its kind of grammatical structure. But I think the thing that ChatGPT is showing us is that there's an additional kind of regularity to language, which has to do with the meaning of the language beyond just this pure, part of speech combination type of thing. And I think the kind of the one example of that we've had in the past is logic. And, I think my sort of kind of picture of how was logic invented, how was logic discovered, it really was a thing that was discovered in its original conception. It was discovered presumably by Aristotle, who kind of listened to a bunch of people, orators, giving speeches. And this one made sense, that one doesn't make sense. This one, and, you see these patterns of, if the, I don't know what, if the Persians do this, then the this does that, et cetera, et cetera, et cetera. And what Aristotle realized is there's a structure to those sentences, there's a structure to that rhetoric that doesn't matter whether it's the Persians and the Greeks or whether it's the cats and the dogs. It's just, P and Q. You can abstract from the details of these particular sentences. You can lift out this kind of formal structure, and that's what logic is.
That's a heck of a discovery, by the way, logic. You're making me realize now.
Yeah.
It's not obvious.
The fact that there is an abstraction from natural language that has where you can fill in any word you want is a very interesting discovery. Now, it took a long time to mature. I mean, Aristotle had this idea of syllogistic logic, where there were these particular patterns of how you could argue things, so to speak. And, in the Middle Ages, part of education was you memorized the syllogisms. I forget how many there were, but 15 of them or something, and they all had names. They all had mnemonics. Like I think Barbara and Celerant were two of the mnemonics for the syllogisms. And people would this is a valid argument because it follows the Barbara syllogism, so to speak. And it took until 1830, with George Boole to get beyond that and see that there was a level of abstraction that was beyond this particular template of a sentence, so to speak. And that's, what's interesting there is, in a sense, ChatGPT is operating at the Aristotelian level. It's essentially dealing with templates of sentences. By the time you get to Boole and Boolean algebra and this idea of, you can have arbitrary depth-nested collections of ands and ors and nots, and you can resolve what they mean, that's the kind of thing, that's a computation story. That's, you've gone beyond the pure sort of templates of natural language to something which is an arbitrarily deep computation. But the thing that I think we realize from ChatGPT is, Aristotle stopped too quickly. Mm-hmm. And there was more that you could have lifted out of language as formal structures. And I think there's, in a sense, we've captured some of that in some of what is in language. There's a lot of kind of little calculi, little algebras of what you can say, what language talks about. I mean, whether it's, I don't know, if you say, I go from place A to place B to place C, then I know I've gone from place A to place C. If A is a friend of B and B is a friend of C, it doesn't necessarily follow that A is a friend of C. These are things that are, that there are, if you go from place A to place B to place C, it doesn't matter how you went. Like logic, it doesn't matter whether you flew there, walked there, swam there, whatever. This transitivity of where you go is still valid. And there are many kinds of features, I think, of the way the world works that are captured in these aspects of language, so to speak. And I think what ChatGPT effectively has found, just like it discovered logic, people are really surprised it can do these logical inferences. It discovered logic the same way Aristotle discovered logic, by looking at a lot of sentences effectively and noticing the patterns in those sentences.
But it feels like it's discovering something much more complicated than logic. So this kind of semantic grammar, I think you wrote about this. Maybe we can call it the laws of language, I believe you call, or which I like, the laws of thought.
Yes. That was the title that George Boole had for his Boolean algebra back in 1830. But yes,
laws of thought.
Yes, that was what he said.
All right.
So he thought he nailed it with Boolean algebra.
Yeah,
there's more to it.
And it's a good question. How much more is there to it? And it seems like one of the reasons, as you imply, that the reason ChatGPT works, is that there's a finite number of things to it.
Yeah, I mean,
it's discovering the laws. In some sense, GPT is discovering the laws of semantic grammar that underlies language.
Yes. And what's sort of interesting is, in the computational universe, there's a lot of other kinds of computation that you could do. Mm-hmm. They're just not ones that we humans have cared about and operate with. And that's probably because our brains are built in a certain way. And, the neural nets of our brains are not that different in some sense from the neural nets of a large language model. And that's and so when we think about, and, maybe we can talk about this some more, but when we think about sort of what will AIs ultimately do, the answer is, insofar as AIs are just doing computation, they can run off and do all these kinds of crazy computations. But the ones that we sort of have decided we care about is this kind of very limited set.
That's where the reinforcement learning with human feedback seems to come in. The more the AIs say the stuff that kind of interests us, the more we're impressed by it. So it can do a lot of interesting, intelligent things, but we're only interested in the AI systems when they communicate in a human-like way.
Yes.
About human-like topics.
Yes. Well, it's like technology. I mean, in a sense, the physical world provides all kinds of things. There are all kinds of processes going on in physics. Only a limited set of those are ones that we capture and use for technology, because they're only a limited set where we say, this is a thing that we can sort of apply to the human purposes we currently care about. I mean, you might have said, okay, you pick up a piece of rock You say, okay, there's a nice silicate. It contains all kinds of silicon. I don't care. Then you realize, oh, we could actually turn this into a semiconductor wafer and make a microprocessor out of it. And then we care a lot about it.
Yes.
And it's this thing about what do we, in the evolution of our civilization, what things do we identify as being things we care about? I mean, it's like, when there was a little announcement recently of the possibility of a high temperature superconductor that involved, the element lutetium, which, generally nobody has cared about.
Yes.
And, it's kind of, but suddenly if there's this application that relates to kind of human purposes, we start to care a lot.
So given your thinking that GPT may have discovered inklings of laws of thought, do you think such laws exist? Can we linger on that?
Yeah.
What's your intuition here?
Oh, definitely. I mean, the fact is, look, the logic is but the first step. There are many other kinds of calculi about things that we consider, about sort of things that happen in the world or things that are meaningful.
Well, how do you know logic is not the last step? You know what I mean? So,
because we can plainly see that their thing. I mean, if you say, here's a sentence that is syntactically correct, okay? You look at it and you're like, the happy electron, ate, I don't know what, something that you look at it and it's like, this is meaningless. It's just a bunch of words. It's syntactically correct. The nouns and the verbs are in the right place, but it just doesn't mean anything. And so there clearly is some rule that there are rules that determine when a sentence has the potential to be meaningful that go beyond the pure parts of speech syntax. And so the question is, what are those rules? And are there a fairly finite set of those rules? My guess is that there's a fairly finite set of those rules. And once you have those rules, you have a kind of a construction kit. Just like the rules of syntactic grammar give you a construction kit for making syntactically correct sentences, so you can also have a construction kit for making semantically correct sentences. Those sentences may not be realized in the world. I mean, I think, the elephant flew to the moon.
Yeah.
Semantically, we have an idea. If I say that to you, you kind of know what that means. But the fact is, it hasn't been realized in the world, so to speak.
So semantically correct, perhaps, is things that can be imagined with the human mind. No. Things that are consistent with both our imagination and our understanding of physical reality. I don't know.
Yeah, it's a good question. I mean, it's a good question. It's a good question. I mean, I think it is, given the way we have constructed language, it is things which fit with the things we're describing in language. It's a bit circular in the end, because you can and the sort of boundaries of what is physically realizable. Okay, let's take the example of motion. Okay, motion is a complicated concept. It might seem like it's a concept that should have been figured out by the Greeks, long ago, but it's actually a really pretty complicated concept. Because what is motion? Motion is you can go from place A to place B, and it's still you when you get to the other end, right? You take an object, you move it, and it's still the same object, but it's in a different place. Now, even in ordinary physics, that doesn't always work that way. If you're near a space-time singularity in a black hole, for example, and you take your teapot or something, you don't have much of a teapot by the time it's near the space-time singularity. It's been completely, deformed beyond recognition. But so that's a case where pure motion doesn't really work. You can't have a thing stay the same. But so this idea of motion is something that sort of is a slightly complicated idea. But once you have the idea of motion, you can start, once you have the idea that you're going to describe things as being the same thing but in a different place, that sort of abstracted idea then has, that has all sorts of consequences, like this transitivity of motion, go from A to B, B to C, you've gone from A to C. And that's, so at that level of description, you can have what are sort of inevitable consequences. They're inevitable features of the way you've sort of set things up. And that's, I think, what this sort of semantic grammar is capturing, is things like that. And I think that it's a question of what does the word mean when you say I move from here to there. Well, it's complicated to say what that means. This is this whole issue of is pure motion possible, et cetera, et cetera, et cetera. But once you have kind of got an idea of what that means, then there are inevitable consequences of that idea.
But the very idea of meaning, it seems like there's some words that become, it's like there's a latent ambiguity to them. I mean, it's the word like emotionally loaded words like hate and love.
Right.
It's like what do they mean exactly? So especially when you have relationships between complicated objects, we seem to take this kind of descriptive shortcut to describe like
right.
Object A hates object B. What's that really mean?
Right. Well, words are defined by kind of our social use of them. I mean, it's not, a word in computational language, for example, when we say we have a construct there, we expect that construct is a building block from which we can construct an arbitrarily tall tower. Mm-hmm. So we have to have a very solid building block. And, it turns into a piece of code, it has documentation, it's a whole thing. Mm-hmm. But the word hate, the documentation for that word, well, there isn't a standard documentation for that word, so to speak. It's a complicated thing defined by kind of how we use it. When, if it wasn't for the fact that we were using language, I mean, so what is language at some level? Language is a way of packaging thoughts so that we can communicate them to another mind.
Can these complicated words be converted into something that a computation engine can use?
Right. So I think the answer to that is that what one can do in computational language is make a specific definition. And if you have a complicated word, like let's say the word eat, okay? You'd think, oh, it's a simple word. It's, animals eat things, whatever else. But, you do programming, you say this function eats arguments, mm-hmm. which is sort of poetically similar mm-hmm. to the animal eating things. But if you start to say, well, what are the implications of, the function eating something? Can the function be poisoned? Well, maybe it can actually, but if there's a type mismatch or something in some language, but how far does that analogy go? And it's just an analogy. Yeah. Whereas if you use the word eat in a computational language level, you would define there isn't a thing which you anchor to the kind of natural language concept eat, but it is now some precise definition of that then you can compute things from.
But don't you think the analogy is also precise? Software eats the world. Don't you think there is something concrete in terms of meaning about analogies?
Sure. But the thing that sort of is the first target for computational language is to take sort of the ordinary meaning of things and try and make it precise. Make it sufficiently precise, you can build these towers of computation on top of it. Yeah. So it's kind of like if you start with a piece of poetry and you say, I'm going to define my program with this piece of poetry. Mm-hmm. It's kind of like that's a difficult thing. It's better to say, I'm going to just have this boring piece of prose and it's using words in the ordinary way. Yeah. And that's how I'm communicating with my computer. And that's how I'm going to build this solid building block from which I can construct this whole kind of computational tower.
So there's some sense where if you take a poem and reduce it to something computable, you're going to have very few things left. So maybe there's a bunch of human interaction that's just poetic, aimless nonsense. Well, that's just like recreational, like hamstering a wheel. It's not actually producing anything.
Well, I think that's a complicated thing because, in a sense, human linguistic communication is there's one mind, it's producing language. That language is having an effect on another mind. Yeah. And the question of there's sort of a type of effect that is well-defined, let's say, where, for example, it's very independent of the two minds. That it doesn't, there's communication where it can matter a lot, sort of what the experience of one mind is versus another one, and so on.
Yeah, but what is the purpose of natural language communication?
Well, I think the
versus computational language somehow feels more amenable to the definition of purpose. It's like, yeah, you're given two clean representations of a concept, and you can build a tower based on that.
Right.
Is natural language the same thing but more fuzzy? Or what?
Well, I think the story of natural language, right, and that's the great invention of our species. We don't know whether it exists in other species, but we know it exists in our species. It's the thing that allows you to sort of communicate abstractly from like one generation of the species to another. You can, there is an abstract version of knowledge that can be passed down. It doesn't have to be, genetics. It doesn't have to be, you don't have to apprentice the next species, the next generation of birds to the previous one to show them how something works.
Yeah.
There is this abstracted version of knowledge that can be kind of passed down. Now, that, it still tends to rely, because language is fuzzy, it does tend to rely on the fact that, if we look at some ancient language where we don't have a chain of translations from it until what we have today, we may not understand that ancient language. And we may not understand, its concepts may be different from the ones that we have today. We still have to have something of a chain, but it is something where we can realistically expect to communicate abstract ideas. And that's one of the big roles of a language. I think, it's, and that's been this ability to sort of concretify abstract things is what language has provided.
Do you see natural language and thought as the same? The stuff that's going inside your mind?
Well, that's been a long debate in philosophy.
It seems to become more important now when we think about how intelligent GPT is.
Whatever that means.
Whatever that means, but it seems like the stuff that's going on in the human mind seems something like intelligence.
Yes.
And his language.
Well, we call it intelligence.
Yeah, yes. And so you start to think of, okay, what's the relationship between thought, the language of thought, the laws of thought, the laws of then words like reasoning, and the laws of language, and how that has to do with computation, which seems like more rigorous, precise ways of reasoning.
Right, which are beyond human. I mean, much of what computers do, humans do not do. I mean, you might say...
Humans are a subset,
yes,
presumably.
Yes.
Hopefully.
Yes. Yes, right. You might say, who needs computation when we have large language models? Large language models can just, eventually you'll have a big enough neural net, it can do anything. Mm-hmm. But they're really doing the kinds of things that humans quickly do. And there are plenty of sort of formal things that humans never quickly do. For example, I don't know, some people can do mental arithmetic. They can do a certain amount of math in their minds. I don't think many people can run a program in their minds of any sophistication. Mm-hmm. It's just not something people do. It's not something people have even thought of doing, because it's kind of not, you can easily run it on a computer.
When an arbitrary program.
Yeah.
Aren't we running specialized programs?
Yeah. But if I say to you, here's
program.
A Turing machine,
yeah,
tell me what it does after 50 steps. And you're like trying to think about that in your mind. That's really hard to do. It's not what people do. I mean,
in some sense, people they build a computer, they program it just to answer your question about what the system does after 50 steps. I mean, humans build computers.
Yes, so, that's right. But they've created something which is then when they run it, it's doing something different than what's happening in their minds. I mean, they've outsourced that piece of computation from something that is internally happening in their minds to something that is now a tool that's external to their minds.
So, by the way, humans to you didn't invent computers; they discovered them.
They discovered computation,
which
they invented the technology of computers.
The computer is just a kind of way to plug into this stream of computation. There's probably other ways. There's probably a lot
for
of
sure.
ways.
I mean, the particular ways that we make computers out of semiconductors and electronics and so on, that's the particular technology stack we built. I mean, the story of a lot of what people try to do with quantum computing is finding different sort of underlying physical, infrastructure for doing computation. Biology does lots of computation. It does it using an infrastructure that's different from semiconductors and electronics. Mm-hmm. It's a molecular scale sort of computational process that hopefully we'll understand more about. I have some ideas about understanding more about that, but that's another it's another representation of computation. Things that happen in the physical universe at the level of these evolving hypergraphs and so on. That's another sort of implementation layer for this abstract idea of computation.
So if GPT or large language models are starting to develop or implicitly understand the laws of language and thought, do you think they can be made explicit?
Yes.
How?
With a bunch of effort. I mean,
so
it's like doing natural science. I mean, what is happening in natural science? You have the world that's doing all these complicated things, and then you discover, Newton's laws, for example. This is how motion works. This is the way that this particular sort of idealization of the world, this is how we describe it in a simple, computationally reducible way. And I think it's the same thing here. There are sort of computationally reducible aspects of what's happening that you can get a kind of narrative theory for, just as we've got narrative theories in physics and so on.
Do you think it will be depressing or exciting when all the laws of thought are made explicit, human thought are made explicit?
I think that once you understand computational irreducibility, it's neither of those things. Because the fact is, people say, for example, people will say, "Oh, but I have free will. I kind of I operate in a way that is they have the idea that they're doing something that is sort of internal to them, that they're figuring out what's happening. But in fact, we think there are laws of physics that ultimately determine, every nerve, every electrical impulse in a nerve and things like this. So you might say, isn't it depressing that we are ultimately just determined by the rules of physics, so to speak? It's the same thing. It's at a higher level. It's like it's a shorter distance to get from kind of semantic grammar to the way that we might construct a piece of text than it is to get from individual nerve firings to how we construct a piece of text. But it's not fundamentally different. And by the way, as soon as we have this kind of level of, this other level of description, it helps us to go even further. So we'll end up being able to produce more and more complicated kinds of things that, just like when we, if we didn't have a computer and we knew certain rules, we could write them down, we'd go a certain distance. But once we have a computer, we can go vastly further. And this is the same kind of thing.
You wrote a blog post titled, "What is ChatGPT doing and why does it work?" We've been talking about this, but can we just step back and linger on this question? What's ChatGPT doing? What are these a bunch of billion parameters trained on a large number of words? Why does it seem to work again? Is it because to the point you made that there's laws of language that can be discovered by such a process? Is there something more to it?
Let's talk about sort of the low level of what ChatGPT is doing. Yeah. I mean, ultimately, you give it a prompt, it's trying to work out, what should the next word be, right?
Which is wild. Isn't that surprising to you that this kind of low level, dumb training procedure can create something syntactically correct first and then semantically correct second?
The thing that has been sort of a story of my life is realizing that simple rules can do much more complicated things than you imagine. That something that starts simple to describe can grow a thing that is, vastly more complicated than you can imagine. Yeah. And honestly, it's taken me, I don't know, I've sort of been thinking about this now 40 years or so, and it always surprises me. I mean, even, for example, in our physics project, sort of thinking about the whole universe growing from these simple rules, I still resist because I keep on thinking, how can something really complicated arise from something that simple? Mm-hmm. It just seems, it seems wrong, but yet, the majority of my life I've kind of known from things I've studied that this is the way things work. So yes, it is wild that it's possible to write a word at a time and produce a coherent essay, for example. But it's worth understanding kind of how that's working. I mean, it's kind of like if it was going to say, the cat sat on the, what's the next word? Okay, so how does it figure out the next word? Well, it's seen 1 trillion words written on the internet. and it's seen the cat sat on the floor, the cat sat on the sofa, the cat sat on the whatever. So its minimal thing to do is just say, let's look at what we saw on the internet. We saw, 10,000 examples of the cat sat on the. What was the most probable next word? Let's just pick that out and say that's the next word. And that's kind of what it at some level is trying to do. Now, the problem is there isn't enough text on the internet to for if you have a reasonable length of prompt to that specific prompt will never have occurred on the internet. And as you kind of go further, there just won't be a place where you could have trained, where you could just worked out probabilities from what was already there. Like if you say 2 + 2, there'll be a zillion examples of 2 + 2 equaling 4, and a very small number of examples of 2 + 2 = 5, and so on. And you can pretty much know what's going to happen. So then the question is, well, if you can't just work out from examples what's going to happen, just no probabilistic from examples what's going to happen, you have to have a model. And there's kind of this idea of making models of things is an idea that really, I don't know, I think Galileo probably was one of the first people who sort of worked this out. I mean, it's kind of like I think I gave an example of that, the little book I wrote about ChatGPT, where it's kind of like, Galileo was dropping cannonballs off the different floors of the Tower of Pisa. And it's like, okay, you drop a cannonball off this floor, you drop a cannonball off this floor, you miss floor 5 or something for whatever reason. But the time it took the cannonball to fall to the ground from floors 1, 2, 3, 4, 6, 7, 8, for example. Then the question is, can you work out, can you make a model which figures out how long would it take the ball to fall to the ground from the floor you didn't explicitly measure? And the thing Galileo realized is that you can use mathematical formulas to make a model for how long it will take the ball to fall. So now the question is, well, okay, you want to make a model for example, something much more elaborate, like you've got this arrangement of pixels, and is this arrangement of pixels an A or a B? Does it correspond to something we'd recognize as an A or a B? And you can make a similar kind, each pixel is like a parameter in some equation, and you could write down this giant equation where the answer is either, A or, 1 or 2, A or B. And the question is then, what kind of a model successfully reproduces the way that we humans would conclude that this is an A and this is a B? If there's a complicated extra tail on the top of the A, would we then conclude something different? What is the type of model that maps well into the way that we humans make distinctions about things? And the big kind of meta discovery is neural nets are such a model. It's not obvious they would be such a model. It could be that human distinctions are not captured. We could try searching around for a type of model that could be a mathematical model. It could be some model based on something else that captures kind of typical human distinctions about things. It turns out this model that actually is very much the way that we think the architecture of brains works, that perhaps not surprisingly, that model actually corresponds to the way we make these distinctions. And so, the core next point is that the kind of model, this neural net model, makes sort of distinctions and generalizes things in sort of the same way that we humans do it. And that's why when you say, the cat sat on the green blank, even though it didn't see many examples of the cat sat on the green whatever, it can make or the aardvark sat on the green whatever. I'm sure that particular sentence does not occur on the internet. And so it has to make a model that concludes what, it has to kind of generalize from the actual examples that it's seen. And so that's the fact is that neural nets generalize in the same kind of a way that we humans do. If we were, the aliens might look at our neural net generalizations and say, that's crazy. That thing, when you put that extra little dot on the A, that isn't an A anymore. That's, that messed the whole thing up. But for us, humans, we make distinctions which seem to correspond to the kinds of distinctions that neural nets make. So then, the thing that is just amazing to me about ChatGPT is how similar the structure it has is to the very original way people imagined neural nets might work back in 1943. Okay. And, there's a lot of detailed engineering, great cleverness, but it's really the same idea. And in fact, even the sort of elaborations of that idea where people said, let's put in some actual particular structure to try and make the neural net more elaborate, to be very clever about it. Most of that didn't matter. I mean, there's some things that seem to, when you train this neural net, the one thing, this kind of transformer architecture, this attention idea, that really has to do with, does every one of these neurons connect to every other neuron, or is it somehow causally localized, so to speak? Does it like we're making a sequence of words and the words depend on previous words rather than just everything can depend on everything? And that seems to be important in just organizing things so that you don't have a sort of a giant mess. But the thing worth understanding about what is ChatGPT in the end? I mean, what is a neural net in the end? A neural net in the end is each neuron has it's taking inputs from a bunch of other neurons. It's eventually going to have a numerical value. It's going to compute some number, and it's saying, I'm going to look at the neurons above me. It's kind of a series of layers. It's going to look at the neurons above me, and it's going to say, what are the values of all those neurons? Then it's going to add those up and multiply them by these weights. And then it's going to apply some function that says if it's bigger than 0 or something, then make it 1, and otherwise make it 0, or some slightly more complicated function. You know very well how this works.
It's a giant equation with a lot of variables. You mentioned figuring out where the ball falls when you don't have data on the fourth floor. The equation here is not as simple as
it's an equation with 175 billion terms.
And it's quite surprising that, in some sense, a simple procedure of training such an equation can lead to
I think
a good representation of natural language.
Right. The real issue is, this architecture of a neural net where what's happening is, you've turned. So neural nets always just deal with numbers. And so, you've turned the sentence that you started with into a bunch of numbers. Like, let's say by mapping, each word of the 50,000 words in English, you just map each word or each part of a word into some number. You feed all those numbers in, and then the thing is and then those numbers just go into the values of these neurons. And then what happens is it's just rippling down, going layer to layer until it gets to the end. I think ChatGPT has about 400 layers. And you're just, it just goes once through. It just every new word it's going to compute just says, here are the numbers from the words before. Let's compute what does it compute? It computes the probabilities that it estimates for each of the possible 50,000 words that could come next. And then it decides, sometimes it will use the most probable word, sometimes it will use not the most probable word. It's an interesting fact that there's this so-called temperature parameter, which, at temperature 0, it's always using the most probable word that it estimated was the most probable thing to come next. If you increase the temperature, it'll be more and more kind of random in its selection of words. It'll go down to lower and lower probability words. The thing I was just playing with actually recently was the transition that happens as you increase the temperature. The thing goes bonkers at a particular, sometimes at a particular temperature. I think maybe about 1.2 is the thing I was noticing from yesterday, actually. Usually it's giving reasonable answers, and then at that temperature, with some probability, it just starts spouting nonsense. And nobody knows why this happens. I mean, and by the way, I mean, the thing to understand is it's putting down one word at a time, but the outer loop of the fact that it says, okay, I put down a word. Now let's take the whole thing I wrote so far, let's feed that back in, let's put down another word. That outer loop, which seems almost trivial, is really important to the operation of the thing. And for example, one of the things that is kind of funky is it'll give an answer, and you say to it, is that answer correct? And it'll say, no. And why is that happening?
It's fascinating, right?
Right. Why can it do that? Well, the answer is because it is going one word at a time, sort of forwards. And it didn't, it came along with some sort of chain of thought in a sense, and it came up with completely the wrong answer. But as soon as you feed it the whole thing that it came up with, it immediately knows that isn't right. It immediately can recognize that was a bad syllogism or something, and can see what happened, even though as it was being led down this garden path, so to speak, it came to the wrong place.
But it's fascinating that this kind of procedure converges to something that forms a pretty good compressed representation of language on the internet.
Yeah.
That's quite.
Right. No,
I'm not sure what to make of it.
Well, look, I think, there are many things we don't understand. Okay. So, for example, 175 billion weights, it's maybe about 1 trillion bytes of information, which is very comparable to the training set that was used. Why it sort of stands to some kind of reason that the number of weights in the neural net, I don't know, I can't really argue that. I can't really give you a good example. In a sense, the very fact that, insofar as there are definite rules of what's going on, you might expect that eventually we'll have a much smaller neural net that will successfully capture what's happening. I don't think the best way to do it is probably a neural net. I think a neural net is what you do when you don't know any other way to structure the thing. And it's a very good thing to do if you don't know any other way to structure the thing. And for the last 2,000 years, we haven't known any other way to structure it. So this is a pretty good way to start. But that doesn't mean you can't find sort of, in a sense, more symbolic rules for what's going on that, much of which will then be, you can kind of get rid of much of the structure of the neural net and replace it by things which are sort of pure steps of computation, so to speak, sort of with neural net stuff around the edges. And that becomes just a much simpler way to do it.
So the neural net, you hope, will reveal to us good symbolic rules that make the need of the neural net less and less and less.
Right. And there will still be some stuff that's kind of fuzzy, just like, there are things that, it's like this question of what can we formalize? What can we turn into computational language? What is just sort of, it happens that way just because brains are set up that way?
What do you think are the limitations of large language models, just to make it explicit?
Well, I think that deep computation is not what large language models do. It's a different kind of thing. The outer loop of a large language model, if you're trying to do many steps in a computation, the only way you get to do that right now is by spooling out, all the whole chain of thought as a bunch of words, basically. And, you can make a Turing machine out of that if you want to. I just was doing that construction. In principle, you can make an arbitrary computation by just spooling out the words, but it's a bizarre and inefficient way to do it. But it's something where I think that's, sort of the deep computation is, it's really what humans can do quickly. Large language models will probably be able to do well. Anything that you can do kind of off the top of your head type thing is really, is good for large language models. And the things you do off the top of your head, you may not get them always right, but, it's thinking it through the same way we do.
But I wonder if there's an automated way to do something that humans do well much faster, to where it like loops. So generate arbitrary large code bases of Wolfram Language, for example.
Well, the question is, what do you want the code base to do?
Escape control and take over the world.
Okay. So, the thing is, when people say, we want to build this giant thing, right? A giant piece of computational language. In a sense, it's sort of a failure of computational language if the thing you have to build, in other words, if we have a description, if you have a small description, that's the thing that you represent in computational language, and then the computer can compute from that.
Yes.
So in a sense, as soon as you're giving a description, if you have to somehow make that description something, definite, something formal, and to say, okay, I'm going to give this piece of natural language, and then it's going to splurt out this giant formal structure. That, in a sense, that doesn't really make sense, because except insofar as that piece of natural language kind of plugs into what we socially know, so to speak, it plugs into kind of our corpus of knowledge, then that's a way we're capturing a piece of that corpus of knowledge, but hopefully we will have done that in computational language. How do you make it do something that's big? Well, you have to have a way to describe what you want.
I can make it more explicit if you want. How about, I just pop into my head, iterate through all the members of Congress and figure out how to convince them that they have to let me, meaning the system, become president. Pass all the laws that allows AI systems to take
Right.
control and be the president. I don't know. So that's a very explicit, like,
Yeah,
figure out the individual life story of each congressman, each senator, anybody. I don't know
Right.
what's required to really kind of pass legislation and figure out how to control them and manipulate them. Get all
Right.
the information. What would be the biggest fear of this congressman? And in such a way that you can take action on it in the digital space. So maybe threaten the destruction reputation or something like this.
Right. If I can describe what I want,
Yeah.
to what extent can a large language model automate that?
With the help of the concretization of something like Wolfram Language, that makes it
Right.
more,
I think
grounded.
it can go rather a long way.
I'm also surprised how quickly I was able to generate
Yeah, right.
an attack.
That's
I swear I did not think about this before, and it's funny how quickly, which is a very concerning thing, because that probably, this idea will probably do quite a bit of damage, and there might be a very large number of other such ideas.
Well, I'll give you a much more benign version of that idea.
Sure.
Okay, you're going to make an AI tutoring system, and that's a benign version of what you're saying is, I want this person to understand this point.
Yes.
You're essentially doing machine learning where the loss function, the thing you're trying to get to is get the human to understand this point. And when you do a test on the human, that they correctly understand how this or that works. And I am confident that sort of the large language model type technology combined with computational language is going to be able to do pretty well at teaching us humans things. And it's going to be an interesting phenomenon because, sort of individualized teaching is a thing that has been kind of a goal for a long time. I think we're going to get that. And I think more, that it has many consequences for, like just, if you know me, if you, the AI, know me, tell me I'm about to do this thing. What are the three things I need to know, given what I already know? Let's say I'm looking at some paper or something, right? It's like there's a version of the summary of that paper that is optimized for me, so to speak, and where it really is, and I think that's really going to work.
It could understand the major gaps in your knowledge.
Yes,
that if filled would actually give you a deeper understanding of the topic. Yeah,
right, and that's an important thing because it really changes. Actually, I think when you think about education and so on, it really changes kind of what's worth doing, what's not worth doing, and so on. It makes I know in my life I've learned lots of different fields, and so I don't know. Every time I'm always think this is the one I'm not going to be able to learn.
yeah.
But turns out there are sort of meta methods for learning these things in the end. And I think this idea that it becomes easier to it becomes easier to be fed knowledge, so to speak, and it becomes if you need to know this particular thing, you can get taught it in an efficient way. Is something I think is sort of an interesting feature, and I think it makes the things like the value of big towers of specialized knowledge become less significant compared to the kind of meta knowledge of sort of understanding kind of the big picture and being able to connect things together. I think that there's been this huge trend of let's be more and more specialized because we have to we have to sort of ascend these towers of knowledge. But by the time you can get more automation of being able to get to that place on the tower without having to go through all those steps, I think it sort of changes that picture.
Interesting. So your intuition is that in terms of the collective intelligence of the species and the individual minds that make up that collective, they will trend towards being generalists and being kind of philosophers.
That's what I think. I think that's where the humans are going to be useful. I think that a lot of these kind of the drilling, the mechanical working out of things is much more automatable. It's much more AI territory, so to speak.
No more PhDs.
Well, it's interesting. Yes, I mean the kind of the specialization, this kind of tower of specialization, which has been a feature of, we've accumulated lots of knowledge in our species, and in a sense, every time we have a kind of automation, a building of tools, it becomes less necessary to know that whole tower, and it becomes something where you can just use a tool to get to the top of that tower. I think that the thing that is ultimately, when we think about, okay, what do the AIs do versus what do the humans do? It's like AIs, you tell them, you say, go achieve this particular objective. Okay, they can maybe figure out a way to achieve that objective. We say, what objective would you like to achieve? The AI has no intrinsic idea of that. It's not a defined thing. That's a thing which has to come from some other entity. And insofar as we are in charge, so to speak, or whatever it is, and our kind of web of society and history and so on is the thing that is defining what objective we want to go to, that's a thing that we humans are necessarily involved in, so to speak.
Well, to push back a little bit, don't you think that future versions of GPT would be able to give a good answer to what objective would you like to achieve?
On what basis? I mean, if they say, look, here's the terrible thing that could happen, okay? They're taking the average of the internet, and they're saying, from the average of the internet, what do people want to do?
Well, that's the Elon Musk adage of the most entertaining outcome is the most likely.
Okay,
so
I haven't heard that one from him. Yeah,
that could be one objective, is maximize global entertainment. The dark version of that is drama. The good version of that is fun.
Right. So I mean, this question of what if you say to the AI, what does the species want to achieve?
Yes.
Okay.
There'll be an answer, right?
There'll be an answer. It'll be what the average of the internet says the species wants to achieve.
Well, that's. I think you're using the word average very loosely there, right? So, I think the answers will become more and more interesting as these language models are trained better and better.
No, but I mean, in the end, it's a reflection back of what we've already said.
Yes, but it's there's a deeper wisdom to the collective intelligence, presumably, than each individual.
Maybe.
Isn't that what we're trying to do as a society?
To have, well, I mean, that's an important, that's an interesting question. I mean, insofar as some of us, work on trying to innovate and figure out new things and so on, it is sometimes it's a complicated interplay between sort of the individual doing the crazy thing off in some spur, so to speak, versus the collective that's trying to do sort of the high inertia average thing. And it's, sometimes the collective, is bubbling up things that are interesting, and sometimes it's pulling down kind of the attempt to make this kind of innovative direction.
But don't you think the large language models will see beyond that simplification, will say maybe intellectual and career diversity is really important? So you need the crazy people on the outlier, on the outskirts. Right. And so like the actual, what's the purpose of this whole thing is to explore through this kind of dynamics that we've been using as a human civilization, which is most of us focus on one thing, and then there's the crazy people on the outskirts doing the opposite of that one thing, and you kind of pull the whole society together. There's the mainstream science, and then there's the crazy science, and that's just been the history of human civilization. And maybe the AI system will be able to see that, and the more and more impressed we are by a language model telling us this, the more control we'll give it to it, and the more we'll be willing to let it run our society. And hence, there's this kind of loop where the society could be manipulated to let the AI system run it.
Right. Well, I mean, look, one of the things that's sort of interesting is we might say we always think we're making progress. Mm-hmm. But yet, if, in a sense, by saying let's take what already exists and use that as a model for what should exist, then, it's interesting that, for example, many religions have taken that point of view. There is a sacred book that got written at time X, and it defines how people should act for all future time. And that's, it's a model that people have operated with. And in a sense, this is a version of that kind of statement. It's like, take the 2023 version of sort of how the world has exposed itself and use that to define what the world should do in the future.
But it's not, it's an imprecise definition, right? Because just like with religious texts and with GPT, the human interpretation of what GPT says will be the perturbation in the system. It'll be the noise. It'll be full of uncertainty. It's not like ChatGPT will tell you exactly what to do. It'll tell you a narrative of what, like it's like a turn the other cheek kind of narrative, right? That's not a fully instructive narrative.
Well, until the AIs control all the systems in the world,
they will be able to very precisely tell you what to do.
Well, they'll do what they'll just do this or that thing, and not only that, they'll be auto-suggesting to each person, do this next, do that next.
Yeah.
So I think it's a slightly more prescriptive situation than one has typically seen. But I think this whole question of sort of what's left for the humans, so to speak, to what extent do we, this idea that there is an existing kind of corpus of purpose for humans defined by what's on the internet and so on, that's an important thing. But then the question of sort of, as we explore what we can think of as the computational universe, as we explore all these different possibilities for what we could do, all these different inventions we could make, all these different things, the question is, which ones do we choose to follow? Those choices are the things that, in a sense, if the humans want to still have kind of human progress, that's what we get to make those choices, so to speak. In other words, there's this idea, if you say, let's take the kind of what exists today and use that as the determiner of all of what there is in the future, the thing that is sort of the opportunity for humans is there will be many possibilities thrown up. There are many different things that could happen or be done. Mm-hmm. And insofar as we want to be in the loop, the thing that makes sense for us to be in the loop doing is picking which of those possibilities we want.
But the degree to which there's a feedback loop, the idea that we're picking something starts becoming questionable because we're influenced by the various systems.
Absolutely.
If that becomes more and more source of our education and wisdom and knowledge.
Right. The AIs take over. I mean, I've thought for a long time that, it's the, AR auto-suggestion that's really the thing that makes the AIs take over. It's just then the humans just follow,
Yeah. We will no longer write emails to each other. We'll just send the auto-suggested email.
Yeah. Yeah. But the thing where humans are potentially in the loop is when there's a choice. And when there's a choice which we could make based on our kind of whole web of history and so on.
Yeah.
And that's, that's insofar as it's all just, determined, the humans don't have a place. And by the way, I mean, at some level, it's all kind of a complicated philosophical issue because at some level, the universe is just doing what it does. We are parts of that universe that are necessarily doing what we do, so to speak. Yet we feel we have sort of agency in what we're doing. And that's its own separate kind of interesting issue.
And we also kind of feel like we're the final destination of what the universe was meant to create. But we very well could be, and likely are, some kind of intermediate step, obviously.
Yeah.
Well, we're most certainly some intermediate step. The question is if there's some cooler, more complex, more interesting thing that's going to be materialized.
The computational universe is full of such things.
But in our particular pocket, specifically, if this is the best we're going to do or not, that's kind of
we can make all kinds of interesting things in the computational universe. When we look at them, we say, yeah, that's a thing. It doesn't really connect with our current way of thinking about things. I mean, it's like in mathematics. Mm-hmm. We've got certain theorems. There are about 3 or 4 million that human mathematicians have written down and published and so on. But there are an infinite number of possible mathematical theorems. We just go out into the universe of possible theorems and pick another theorem. And then people will say, well, that's they look at it and they say, I don't know what this theorem means. It's not connected to the things that are part of kind of the web of history that we're dealing with. I think one point to make about sort of understanding AI and its relationship to us is, as we have this kind of whole infrastructure of AIs doing their thing and doing their thing in a way that is perhaps not readily understandable by us humans, you might say that's a very weird situation. How come we have built this thing that behaves in a way that we can't understand, that's full of computational irreducibility, et cetera, et cetera, et cetera? What is this? What's it going to feel like when the world is run by AIs whose operations we can't understand? And the thing one realizes is, actually, we've seen this before. That's what happens when we exist in the natural world. The natural world is full of things that operate according to definite rules. They have all kinds of, computational irreducibility. We don't understand what the natural world is doing. Occasionally, when you say, are the AIs going to wipe us out, for example? Well, it's kind of like, is the machination of the AIs going to lead to this thing that eventually comes and destroys the species? Mm-hmm. Well, we can also ask the same thing about the natural world. Are the machination of the natural world going to eventually lead to this thing that's going to, make the Earth explode or something like this? Those are questions. And insofar as we think we understand what's happening in the natural world, that's a result of science and natural science and so on. One of the things we can expect when there's this giant infrastructure of the AIs is that's where we have to kind of invent a new kind of natural science that kind of is the natural science that explains to us how the AIs work. It's kind of like we have a horse or something, and we're trying to ride the horse and go from here to there. We don't really understand how the horse works inside, but we can get certain rules and certain, approaches that we take to persuade the horse to go from here to there and take us there. And that's the same type of thing that we're kind of dealing with the sort of incomprehensible, computationally irreducible AIs. But we can identify we can find these kind of pockets of reducibility that we can kind of, we're grabbing onto the mane of the horse or something to be able to ride it, or we figure out, if we do this or that to ride the horse, that's a successful way to get it to do what we're interested in doing.